The industrialization of biology, mass cultivation and processing. Technological disruption serves as the final operational bridge of the human-specific anomaly, executing the transition from a bounded biological entity to a standardized mechanical weapon. In natural systems, microscopic pathogens are strictly constrained by physical and environmental limitations. Relying on random contact kinetics, microclimate, weather conditions, or fragile vectors to execute transmission, anthropocentric intervention removes these evolutionary boundaries. By applying advanced physics, industrial engineering, and material science, human systems convert fragile biological entities into mass-scale strategic weapons capable of altering geopolitical power dynamics. This process begins with the industrialization of biology, transforming unpredictable living cultures into uniform military materials. While natural pathogens replicate within the limited, self-regulating confines of a host body or localized environmental niches, modern industrial microbiology bypasses these restrictions through automated bioreactor scale-up. Industrial fermentation arrays maintain computerized control over pH balances, dissolved oxygen saturation, and nutrient gradients, permitting the rapid generation of metric tons of highly concentrated pathogenic slurry. This unit transforms this crude material into an effective weapon. Scientists utilize precision micromilling and particle size optimization. In their natural state, microscopic viral and bacterial particles exhibit electrostatic attraction, causing them to aggregate into large clumps that fall harmlessly to the ground. Human weaponization programs resolve this limitation by deploying advanced milling technologies paired with chemical anti-caking additives, such as fumed silica. This intervention guarantees that the resulting particles are uniform in size, specifically tracking between 1 and 5 microns. Within this precise physical range, the biological material behaves aerodynamically like a gas, staying suspended in atmospheric currents for long periods and bypassing the host's primary upper respiratory filtration systems to deposit directly into the deep lung tissue. Finally, this material is subjected to advanced lyophilization or freeze drying, by sublimation extracting water from the pathogen's cellular or viral structure without disrupting its structural integrity. Volatile living cultures are converted into highly stable powders. This process allows highly dangerous agents to be stockpiled in weapon systems for years without experiencing metabolic degradation or losing their strategic potency. The physics of dispersal, bypassing natural vectors. The true hallmark of technological disruption is the development of artificial delivery systems that replace nature's slow and inefficient transmission methods with precise engineered physics. This mechanical intervention operates through two primary modalities: line source aerosol generation and explosive point source munitions, both augmented by microencapsulation. In natural systems, respiratory pathogens spread through close personal contact, such as coughing or sneezing, which severely limits the geographic footprint of an outbreak. Line source dispersal removes this constraint by releasing stabilized biological agents from a moving platform, such as an aircraft, automated drone, or marine vessel, traveling perpendicular to prevailing wind currents. This technique generates a massive invisible cloud of pathogens that drifts downwind over entire metropolitan areas or military fronts. By exploiting atmospheric diffusion, line source delivery infects thousands of individuals simultaneously over hundreds of square kilometers, expanding the epidemiological footprint far beyond natural boundaries. When strategic constraints require localized targeting, weapon designers deploy explosive point source munitions. Standard high explosives generate intense thermal energy and violent shock waves that instantly destroy cellular life, rendering conventional artillery or missile casings useless for biological payloads. To resolve this physics constraint, military engineers deployed low-velocity bursting charges and pressurized gas dissemination systems. These specialized munitions rupture the outer casing gently, utilizing controlled kinetic energy to turn the internal liquid or powder agent into an immediate, concentrated aerosol cloud without exposing the active microbes to lethal heat or structural shear forces. To ensure these artificial clouds survive environmental exposure, the pathogen is retrofitted with microencapsulation. Open-air environments naturally degrade pathogens through ultraviolet radiation, ambient heat, and atmospheric pollution. Microencapsulation coats individual microbes in microscopic layers of protective polymers or protective sugars, such as tree halos. This chemical coating acts as a suit of physical armor, shielding the organism's metabolic or structural core from environmental decay and keeping it alive long enough to locate and infiltrate a host organism. The strategic transformation from germs to geopolitics. When technology removes the physical limits of a pathogen, the organism ceases to be an isolated medical concern and transforms into a major strategic asset that alters human conflict. This shift facilitates strategic and asymmetric deterrence because biological weapons require significantly less financial investment and industrial infrastructure to produce than nuclear options. They function as a highly effective equalizer, often referred to as the poor man's atomic bomb. This affordability allows smaller nations or non-state actors to establish a powerful strategic deterrent against technologically superior adversaries, disrupting conventional military power balances. This strategic utility is enhanced by the capacity for plausible deniability and covert exploitation. Unlike a conventional missile strike or a nuclear detonation, which leaves clear forensic signatures, an engineered biological attack can be deliberately disguised as a natural, spontaneous epidemic. By deploying a pathogen characterized by a prolonged, asymptomatic incubation period, an adversary can quietly weaken a nation's labor force, agricultural stability, or military readiness. This temporal delay makes it difficult to definitively identify the attacker or justify state-level military retaliation. Potent psychosocial retaliation, changing the rules of modern warfare. Ultimately, this technological disruption culminates in a potent psychosocial weapon. The invisible, transmissible nature of biological agents ensures that their deployment triggers widespread panic, paranoia, and a systematic breakdown of social trust. The psychological toll of an invisible threat forces targeted governments to divert massive amounts of civil and economic resources toward quarantine enforcement, medical containment, and public order. This internal strain can effectively paralyze a target nation's decision-making apparatus without destroying its physical infrastructure. This capacity for a runaway, uncoupled destruction provides the clear evidence of the resource-heavy Homo colossus footprint, showing how human technological intervention overrides Gaia's self-regulating equilibrium and sets the stage for the deep-seated transgenerational trauma outlined in my unified hypothesis. Chapter 2. War and Slavery Across Kingdoms. The Anthropomorphic Trap. Defining war and slavery in biological terms. Biology must systematically avoid the anthropomorphic trap, the pervasive cognitive bias of projecting human consciousness, intentionality, and moral architectures onto non-human organisms. In the natural world, phenomena analogous to human warfare and systemic enslavement are neither ideological choices nor products of moral degeneracy. Instead, they manifest as highly evolved, genetically hard-coded metabolic strategies driven by structural resource scarcity and the optimization of evolutionary fitness. By demoralizing the biological vocabulary, science shifts away from the era of intentionality, which incorrectly attributes cruelty, malice, or geopolitical ambition to organisms executing destructive survival programs. Natural selection operates as a strict thermodynamic ledger. A biological lineage survives, stabilizes and propagates across deep time only if its cumulative caloric and reproductive output exceeds its total metabolic investment. When stripped of anthropocentric framing, war can be defined biologically as high-density, group-level lethal aggression executed between non-kin colonies or distinct species, driven primarily by the acquisition of territorial or reproductive resources. The critical kinetic marker of natural warfare is the expression of extreme intergroup altruism, where an individual organism sacrifices their own survival to secure genetic or caloric dominance over the collective gene pool. Similarly, the biological definition of slavery, classified scientifically as doulosis or aggressive social parasitism, diverges sharply from human institutionalized ownership. In nature, it represents the interspecific or intraspecific appropriation of another organism's somatic labor, metabolic output, or reproductive capacity through behavioral manipulation or chemical coercion. The defining kinetic marker of biological slavery is the absolute diversion of the host organism's energetic budget toward a non-kin lineage. This results in a net evolutionary fitness cost of 0 for the host's own genes, redirecting its life-sustaining adenosine triphosphate, ATP, to manufacture the genetic legacy of its exploiter. The structural dimensions of non-human war. Group-level lethal conflict is an exceptionally rare behavioral paradigm in the biosphere, emerging almost exclusively within highly integrated social lineages where high population densities create intense, unyielding resource pressures. Within this superorganism kinetics, observed in eusocial insects like formica ants or complex mammalian groups like pan-troglodytes, a colony or troop functions as a single evolutionary unit. In these systems, collective aggression operates as an expansionist mechanism to secure critical foraging grounds, nesting architectures, or reproductive territory. When a group's demographic density exceeds the immediate carrying capacity of its local microenvironment, the collective unit faces a stark evolutionary bottleneck. It must either succumb to metabolic starvation or violently displace adjacent non-kin populations. Converting coordinated group aggression into a primary survival pressure, this unyielding pressure has driven the morphological specialization of distinct sacrificial soldier castes within eusocial lineages, such as the Termitidae. Natural selection has engineered physical weaponry directly into the host anatomy, producing oversized mandibles, specialized crushing armor, or frontal defensive glands designed for chemical spray delivery. These adaptations frequently render the soldier class incapable of self-feeding, locking them into an obligate dependence on the worker caste while optimizing them exclusively for collective combat. The underlying evolutionary mechanics of this self-destructive behavior are resolved via Hamilton's rule, which dictates that altruistic lethal combat stabilizes when the genetic relatedness between the sacrificing individual and the beneficiary collective multiplies the fitness benefit to outbalance the direct reproductive costs incurred by the individual. Because worker and soldier ants share highly related genetics with their maternal queen, charging into lethal intercolony battles maximizes their indirect evolutionary fitness, allowing highly organized warfare to persist as an ecologically stable strategy millions of years before the arrival of human consciousness. The structural dimensions of biological slavery. Natural slavery operates entirely without the implementation of physical chains or whips, relying instead on evolutionary loopholes, precise cuticular biochemistry, and sensory hijacking to force host species into self-destructive submission. This exploitation is vividly illustrated by doulosis, or slave-making behaviors, among highly specialized ant species such as the Amazon ant, Polyergus rufescens. These raiders have evolved highly specialized mandibles optimized exclusively for lethal combat, leaving them anatomically incapable of foraging for nutrients, constructing nests, or nursing their own brood. To resolve this metabolic deficit, the colony executes highly organized, coordinated military raids on neighboring Formica nests. During these assaults, the raiders deploy chemical alarm pheromones to scatter the adult host population, systematically capturing the defenseless host pupae and transporting them back to the raiders' nesting hub. The success of this systemic exploitation relies on post-eclosion chemical imprinting. When the captured pupae hatch within the raiders' nest, they encounter a controlled chemical landscape dominated by the raiders' cuticular hydrocarbons. Misidentifying this environment as their native colony, the newly emerged workers imprint on the raiders' chemical profile, spending their entire somatic life cycles foraging for food, maintaining the physical nest, and rearing the raiders' offspring. They remain completely blind to the reality that they are operating as a genetic dead end. This sensory hijacking is mirrored in avian lineages through brood parasitism, exemplified by the common cuckoo, Cuculus canorus. The female cuckoo clandestinely deposits her eggs into the nests of smaller host species, matching the host egg's coloration through rapid evolutionary adaptation. Upon hatching, the cuckoo chicken instinctively ejects the host's natural eggs and hatchlings from the nest, securing an absolute monopoly over parental investment. The parasite then triggers a state of sensory overdrive, emitting hyper-frequent begging calls that mimic the auditory signature of an entire hungry brood. Trapped by their own hard-coded nesting instincts, the host parents exhaust their metabolic reserves to feed a giant parasite that will never pass on their genes, demonstrating how biological slavery exploits behavioral software to harvest the energy of another species. This manipulation reaches its peak in zombie kinetics, where parasites actively rewrite the neurological programming of their hosts to force behavioral self-destruction. The parasitic hairworm, Spinochoroides tellini, infects the terrestrial grasshopper, developing inside its body cavity and absorbing its internal nutrients. Upon reaching reproductive maturity, the worm synthesizes specialized effector proteins that directly alter the host central nervous system, overriding its natural survival programming. This biochemical manipulation forces the land-dwelling insect to abandon its ecological niche, march toward an open water source, and dive in to drown. This induced suicide allows the adult hairworm to emerge into its native aquatic environment to complete its reproductive cycle, illustrating how natural parasites can completely dismantle a host's behavioral software to serve their own evolutionary lineage. The metric of energy, the ledger of exploitation. By systematically stripping away human moral language and ideological projections, cross-kingdom exploitation can be precisely quantified using a universal thermodynamic ledger. Every living organism operates under a finite energy budget, derived from the accumulation of adenosine triphosphate, ATP, which must be continuously distributed across three primary biological sectors: maintenance, growth, and reproduction. Biological warfare and natural slavery represent the forceful, systemic extraction of this energy budget by an outside genetic lineage. This thermodynamic theft can be modeled by analyzing the absolute divergence in evolutionary fitness. The exploiting lineage experiences a sharp spike in reproductive success because it successfully shifts the energetic burdens of foraging, nesting infrastructure, and brood care onto an external workforce. Conversely, the exploited host population experiences an absolute drop in fitness, as its lifetime accumulation of cellular energy is completely spent building the genetic legacy of its predator or master. In natural ecosystems, this energetic extraction is kept in check by density-dependent constraints and coevolutionary bounds, preventing any single exploiting species from achieving permanent dominance. It is only with the emergence of the resource-heavy Homo colossus that this ledger has become unsustainably uncoupled, allowing human technological exploitation to override these biospheric limits and anchor the deep-seated transgenerational trauma outlined in my unified hypothesis. Resource scarcity and the thermodynamic calculus. The emergence of group-level violence and structural exploitation across non-human kingdoms is governed by strict mathematical and ecological imperatives. Far from being biological aberrations, these behaviors represent predictable evolutionary strategies that arise under specific environmental and genetic conditions. Every organism operates as a bounded thermodynamic system that must capture more energy from its surrounding environment than it expends on survival, somatic maintenance, and reproductive output. When resources are abundant, the metabolic cost of independent production and passive foraging remains low, favoring peaceful coexistence. However, localized resource scarcity fundamentally alters the cost-benefit analysis of resource acquisition, forcing a strategic pivot from independent survival to predatory extraction. When essential resources are limited, the systemic exploitation of an adjacent population often yields a higher return on metabolic investment than independent labor. This strategic shift is precisely modeled by Jerome Brown's economic defensibility model, which dictates that territorial aggression or social dominance will only evolve when the energy secured by defending or stealing a resource outbalances the metabolic and physical costs of combat. Consequently, collective warfare and social slavery do not emerge in environments characterized evenly distributed, low-value resources, such as open grazing fields where independent consumption is highly efficient. Instead, these phenomena evolve exclusively around highly concentrated, localized patches of energy, such as a secure subterranean nest site, a high-yield fruit tree, or a dense colony of aphid livestock managed by a competing colony. This dynamic can be quantified through a universal procurement equation. If the energetic expenditure required to forage independently significantly exceeds the kinetic energy and risk investment required to violently seize and establish resources from an adjacent group, natural selection ruthlessly favors the lineage that defaults to combat and systemic exploitation. Genetic relatedness and the mathematics of mass conflict. Group-level warfare presents a profound evolutionary paradox because it requires individual organisms to routinely risk immediate death, a behavior that appears to violate the core tenet of individual survival. In natural systems, this extreme self-sacrifice is structurally impossible without the genetic mechanism of kin selection, which shifts the focus of natural selection from the survival of the individual organism to the survival of the underlying genetic lineage. Coordinated mass conflict requires that participants be bound by high genetic relatedness, transforming the individual into an expendable unit of a larger, collective superorganism. When an individual soldier dies protecting its colony's resources, its personal reproductive fitness collapses to zero. However, because it shares an exceptionally high proportion of its genome with the reproducing queen, its self-sacrificing behavior ensures the survival of hundreds of clonal siblings who carry identical copies of those same altruistic genes. This genetic mathematics creates the foundation for collective defense and expansionist warfare, demonstrating that natural cooperation and group-level violence are two sides of the same evolutionary coin. This deep genetic hard-coding of group-level operation provides the baseline for my unified hypothesis. In nature, this intense cooperation is bound by close genetic kinship to protect the gene pool from external threats. My framework builds directly on this foundation, proposing that Homo sapiens evolved to expand this cooperative mechanism to a species-wide scale, a true eusocial superorganism whose hard-coded cooperative software has been disrupted by ancient transgenerational trauma. Haploidability and the superorganism kinetic. The mathematical imperative driving collective self-sacrifice is uniquely magnified in new social hymenopteran lineages, encompassing ants, bees, and wasps. By the genetic mechanism of haplodiploidy, under this sex determination system, males develop from unfertilized eggs and are completely haploid, carrying only a single maternal set of chromosomes, whereas females develop the fertilized eggs and are fully diploid. This asymmetrical genomic structure fundamentally alters standard Mendelian relationship coefficients. Because full sisters inherit an identical set of chromosomes from their haploid father and share half of their mother's genome, they exhibit a genetic relatedness coefficient of 75%. Remarkably, this makes them significantly more related to one another than they would be to their own potential biological offspring, which is 50%. The strategic outcome of this genetic architecture is that individual worker and soldier lives are rendered evolutionarily cheap, making self-sacrifice the mathematically optimal choice. A soldier ant executing a lethal defensive maneuver on a territorial front line to protect the queen's reproductive output maximizes her own genetic legacy far more effectively than any attempt to fracture from the colony and reproduce independently. This high genetic affinity transforms the individual from an independent agent into an interchangeable component of a larger, cohesive, biological machine. The entire colony functions as a single superorganism capable of organizing and waging total war, coordinating thousands of sterile units to execute complex, high-stakes military strategies that would be biologically impossible in species lacking this intense genetic alignment. The thermodynamic advantage of metabolic exploitation. Whether manifested through social parasitism, brood theft, or structural labor coercion, exploitation provides a highly efficient evolutionary shortcut in the biospheric ledger. This parasitic lifestyle allows an exploiting lineage to completely eliminate the vast metabolic overhead costs of survival by systematically offloading them onto a vulnerable host population. Every independent species is bound to a high maintenance budget, requiring immense daily outputs of cellular energy, ATP, to forage for nutrients, construct physical defenses, and regulate internal cellular health. This high baseline expenditure naturally places a strict ceiling on the energy a lineage can allocate toward direct reproductive output. By transitioning to an exploitive strategy, social parasites like the specialized slave-making ant, Polyergus, systematically shed these capital overhead costs. Over deep evolutionary time, these insects have completely lost the morphological structures and behavioral pathways required to excavate nesting chambers, seek out food sources, or feed their own larvae. By outsourcing these energy-intensive domestic tasks to a captured workforce, the parasitic lineage operates with a near-zero maintenance budget. The systemic freedom allows the parasite to channel its entire metabolic energy reserve into producing high-quality, behaviorally dominant reproductive elites, vastly outbreeding and out-expanding surrounding independent species. Furthermore, this thermodynamic theft enables a process known as evolutionary niche hijacking. Cultivating, adapting to, and securing a novel ecological niche requires millions of years of gradual genetic modification and intense selective pressure. Exploitative species bypass the immense timeline entirely by targeting and hijacking a mature, highly stable niche that has already been perfected by another organism. This systemic infiltration relies on locating and hacking a sensory loophole within the host's evolutionary architecture.